In the realm of artificial intelligence and machine learning, recent advancements have led to the development of large language models like ChatGPT, Claude, and Gemini, as well as diffusion models such as DALL-E 3 and Sora. These foundation models exhibit intriguing properties like in-context learning and chain-of-thought reasoning. However, concerns about their security and privacy have emerged, particularly in distributed or decentralized computing scenarios. Ensuring the integrity of inference results is crucial in machine learning as a service, MLAAS, where service providers must demonstrate to customers that the output stems from inputting the customer's prompt into a verified large language model, such as GPT-4, and generating the response through model execution. This requirement is referred to as model security or model integrity. In distributed or decentralized inference applications, a central server divides a foundation model into distinct segments, each managed by a different party. When an inference query arises, each party executes its segment independently. It is essential to ascertain the trustworthiness of each party's execution before aggregating the outputs. Data privacy issues also arise in decentralized inference, where users need to ensure that their input data are not directly visible to the decentralized nodes that carry the AI inference. Nesa addresses these challenges with a comprehensive framework that utilizes multiple techniques to protect data and model outputs. This includes zero-knowledge proofs for secure model verification, consensus-based verification checks for consistent outputs across nodes, and confirmation of model integrity. Split learning divides models into segments processed by different nodes, preventing full data access at any single point and ensuring data privacy. Trusted execution environments are used for hardware-based security, protecting data and computations within secure zones. Nesa's state-of-the-art proofs and principles demonstrate the framework's effectiveness in securely democratizing artificial intelligence, making it a promising approach for critical inference settings where sensitive information, such as medical records, financial data, or security information, is processed. Ensuring data privacy and security is crucial for the responsible deployment of artificial intelligence across various domains. At Nesa, a hybrid approach to security and privacy is designed to address these concerns, with the selection of methods depending on specific use cases and required levels of security and privacy. Two key scenarios are discussed: critical inference and general inference. Critical inference refers to scenarios where AI inference results are extremely significant, necessitating the highest levels of security and privacy. Examples include healthcare diagnostics and financial decision-making, where sensitive data demands robust privacy measures. To address this, Nesa adapts and innovates two leading technologies: zero-knowledge machine learning, ZKML, for model integrity verification and homomorphic encryption, HE, for data encryption and user privacy protection. Nesa applies state-of-the-art ZKML techniques to build zero-knowledge decentralized proof system, ZKDPS, for proof generation and verification processes in foundation models. Additionally, Nesa proposes sequential vector encryption, SVE, based on sequential homomorphic encryption, SHE, to obfuscate the output of each operator in a neural network. General inference refers to everyday AI inference tasks with less critical results, allowing for faster processing speeds and lower costs without compromising basic security and privacy standards. Examples include routine tasks such as checking the weather or recommending products. Under this scenario, Nesa employs consensus-based verification, CBV, for security and split learning, SL, for data encryption. CBV ensures the integrity of the inference process, while SL provides a reasonable level of data protection. Notably, Nesa has innovated this verification method to reduce redundancy requirements in model verification, and split learning has been used in decentralized AI encryption for the first time. In addition to software and/or algorithm-based security and privacy approaches, Nesa designs an orthogonal hardware-based approach using Trusted Execution Environment (TEs) create secure isolation zones within the network's nodes, protecting user data and private model parameters from unauthorized access. This hardware-based security measure works as an alternative to algorithm-based approaches, providing a fast and efficient solution for Nesa's decentralized AI inference tasks. Nesa's T implementation, NTE, optimizes communication among multiple Ts by establishing direct, secure channels and implementing heterogeneous T scheduling based on node capabilities. This facilitates secure collaboration across multiple nodes, enabling Nesa to maintain high performance, robust security, and data privacy. The technical details of Nesa's security and privacy approaches rely on mathematical concepts such as zero-knowledge proofs, homomorphic encryption, consensus-based verification, and split-learning algorithms. The visual representation of Nesa's security and privacy approaches highlights the trade-offs between security, privacy, and efficiency. The limitations and assumptions of Nesa's security and privacy approaches are discussed, including the computational heaviness of ZKML and HE, and the need for redundant verification in CBV. Future work includes the potential application of Nesa's security and privacy approaches to other domains and scenarios. The security flowchart for critical inference, as depicted in Figure 1, outlines the secure data and model transmission process. User data is transmitted with secure homomorphic encryption, SHI, to Node 1, Node 2, Node K. The sharded AI model inference results are also transmitted via SHI, ensuring secure data and model transmission. The orchestrator retrieves the results from node runners and verifies the AI model using Zero-Knowledge Decentralized Proof System, ZKDPS. Table 1 summarizes the proposed security and privacy solutions, categorizing them into critical and general inference scenarios. For critical inference, ZKDPS is used for model verification, and SHI is employed for data encryption. In contrast, for general inference, consensus-based verification, CBV, is used for model verification, and split learning, SL, is used for data encryption. Additionally, trusted execution environment, T-based solutions can be leveraged as an orthogonal approach, addressing both verification and encryption needs simultaneously. The choice of security and privacy options depends on the scenario. For critical inference, where the final results have high value and users are willing to wait longer, ZKDPS and SHI are recommended. For general inference, where results are less critical and faster processing is desired, CBV and SL are suggested. The TEE-BASED solution, NTE, can also be employed, but it is limited to CPU-BASED solutions, whereas algorithm-based solutions can fully leverage GPUs. By combining both algorithm-based and hardware-based security measures, Nesa provides robust and adaptable security and privacy solutions across a wide range of AI applications, allowing users to select the most appropriate level of protection for their data and applications. This adaptive approach ensures an optimal balance among security, privacy, and performance. In critical inference scenarios, the significance of AI inference results necessitates the highest levels of security and privacy, as the outcomes directly impact crucial sectors like healthcare and finance. The strategy for ensuring model verification and integrity is via ZKDPS, a specialized ZK system for decentralized large language models, LLMs, that allows one party to prove to another that a statement is true without revealing any information beyond the validity of the statement. In the realm of decentralized AI inference, a novel approach has been proposed to enhance the efficiency of zero-knowledge, ZK, proof generation and secure data encryption. This method leverages sequential vector encryption, SVE, to enable computations on encrypted data without decryption, thereby safeguarding sensitive data throughout the inference process. The significance of this approach lies in its ability to protect against deceitful behavior by computing nodes in decentralized environments, which could compromise aggregated results. The threat model in decentralized AI inference involves adversaries exploiting vulnerabilities within the inference systems of foundational models. To counter this, mechanisms are required to enable nodes to provide proofs of honest execution to the central server or public while safeguarding the confidentiality of their models. This necessitates ensuring both the integrity of inference processes and the privacy of model architectures. The proposed approach involves the implementation of mechanisms where central servers solicit proof of computing execution from each node. This process is orchestrated to ensure that while the proof is furnished, the node's confidential model parameters remain undisclosed. The efficacy of this approach hinges upon the successful verification of the proof, serving as a litmus test for the trustworthiness of the node in question. The challenge of fast inference of secure foundation models is also addressed. Given the scale of big data and the models involved, foundation models inherently exhibit slow inference speeds. Incorporating security measures further exacerbates this slowdown in AI models. The proposed approach aims to ensure the security of foundation model inference without compromising efficiency. The problem setup involves decentralized inference for foundation models, which offers numerous benefits, including enhanced device utilization and elimination of the need for data communication between nodes and a central server. However, as foundation models grow in size, it becomes impractical to load entire models on a single node or server. Model decomposition is a core assumption in decentralized AI inference, where the model used in the inference system can be divided into several parts, each managed by a separate party or computing node. The proposed approach is detailed in Section 2.1, which introduces new techniques to speed up the ZK process. Section 2.2 provides more information on the technique of applying implied tensor transformations to selected layers of an AI model. Figure 1 summarizes the security flow of critical inference at Nesa, where data is transmitted with SVE for encryption, and the final inference results are verified by ZKDPS for integrity. Key equations and algorithms involved in the proposed approach include the use of SVE to enable computations on encrypted data without decryption. The mathematical concepts underlying this approach involve the use of homomorphic encryption and zero-knowledge proof systems. The purpose and significance of these concepts are to ensure the security and integrity of decentralized AI inference processes. The proposed approach has several limitations and assumptions, including the assumption that the model used in the inference system can be divided into several parts, each managed by a separate party or computing node. Future work involves exploring the scalability and efficiency of the proposed approach in large-scale decentralized AI inference environments. Verifying the correctness of a circuit's execution relies on three key properties: PV completeness, soundness, and zero-knowledge. PV completeness ensures that a valid circuit is accepted by the verifier, while soundness guarantees that an invalid circuit is rejected. Zero-knowledge proof, as depicted in Figure 2, enables the prover to prove the correctness of the circuit's execution without revealing the witness, which are the secret inputs W1 and W2. In decentralized inference of foundation models, the prover is a computing node that owns a part of the foundation model, while the verifier is the central server that aggregates results from each node. The threat model assumes a semi-dishonest central server that tries to glean additional information about the model weights, while some computing nodes may be dishonest and deviate from the agreed protocol. To guarantee honesty and prevent information leakage, zero-knowledge proofs are employed. This cryptographic technique involves a commitment process, followed by multiple challenge-response interactions between the prover and verifier. In the non-interactive scenario, the Fiat-Shamir heuristic is used to challenge the prover, and the verifier only needs to verify the last response. The zero-knowledge proof process involves three essential steps: commitment, proof, and verification. The prover commits to the witness data, such as model parameters, ensuring its integrity. The proof step involves multiple challenge-response interactions, and the verification step checks the correctness of the proof. In the decentralized inference framework, each computing node performs its assigned computations and sends the results to the central server. The method of decomposition, whether layer-wise or width-wise, depends on the application scenario. The semi-dishonest assumption on the central server implies that it accurately reports the verification result but tries to glean additional information about the model weights. The use of zero-knowledge proofs in this framework ensures that each party is honest about its execution of inference of foundation models without disclosing confidential information. This technique underpins the architecture of blockchain and provides a secure and trustworthy way to verify the correctness of computations in decentralized systems. In the realm of secure multi-party computation, a prover can preserve the confidentiality of sensitive information by encrypting it before transmission to a verifier. This is achieved through the commitment of a d-dimensional tensor S, utilizing the generalized Peterson commitment scheme as expressed in equation 1. This scheme entails sampling random elements from an elliptic curve group G and a scalar field F, then combining them with the tensor S to produce a verifiable commitment. The protocol for secure multi-party computation comprises two primary steps. First, the prover executes the protocol and generates a proof of execution in a finite field F, which is then transmitted to the verifier. Second, the verifier examines the proof to ensure the honest execution of the protocol by the prover, thereby validating the transaction or information under scrutiny. Zero-knowledge proofs possess several advantageous properties, including completeness, special soundness, and zero knowledge. Completeness ensures that if the prover accurately executes the circuit, the proof will be validated with probability 1. Special soundness guarantees that if the prover is dishonest, the proof will fail with high probability. Zero knowledge ensures that the verifier gains no knowledge about the prover's witness. Zero-knowledge proofs can be classified as either interactive or non-interactive, depending on whether the verification process involves a single round or multiple rounds. Non-interactive proof systems, such as those using the Fiat-Shamir heuristic, can be simulated by having the prover generate their own challenge using a random oracle model or a hash function. The resulting non-interactive proof procedure involves the prover computing a challenge using the hash function, and then sending the resulting messages to the verifier for verification. The properties of zero-knowledge proofs ensure that the proof will pass verification only if the prover is honest, while also allowing the prover to keep their secret or witness hidden from the verifier. These properties form the foundation of blockchain and decentralized machine learning, enabling secure and private computation over sensitive information. The Peterson commitment scheme is employed to ensure the binding property, guaranteeing that once the commitment is sent to the verifier, the opening information cannot be altered by the prover. Initially, it appears that the zero-knowledge property may be compromised, as the prover must send the witness S to the verifier to prove the ability to open the commitment. However, the homomorphic property of the Peterson commitment enables the prover to prove this ability without revealing the witness. The homomorphic property allows the prover to combine two commitments, commit S1, R1, and commit S2, R2, corresponding to tensors S1 and S2, respectively, to obtain a new commitment commit S1 plus S2, R1 plus R2. This property enables the prover to prove the ability to open the commitment without revealing the witness by opening a commitment of a linear transformation of the witness S equals SE plus D, where D is a hiding vector and E is a challenge randomly sampled by the verifier. The existence of the challenge E guarantees special soundness, as two runs of the procedure with different challenges E1 and E2 will identify the witness S and the hiding vector D through Gaussian elimination, as demonstrated in equation 2. Algorithm 1 provides a complete procedure for the opening of the commitment, enabling the prover to prove to the verifier that they know a witness S element of FD and a witness T element of F, which are openings of the commitments 1 and 3, respectively, such that S, Y equals T. The algorithm involves the following steps: randomly sampling generators H, G, G1, GD from the elliptic curve group G, which are publicly known to both parties, sending commitments CS and quart to the verifier, picking a hiding vector D and sending commitments CD and CD, Y to the verifier, receiving a challenge E from the verifier, computing S equals SE plus D and RT equals RTE plus R2, sending S, RS, and RT to the verifier, and verifying CS equals CESCD and quart equals CETCD, Y. This algorithm ensures that the prover can prove the ability to open the commitment without revealing the witness, while also guaranteeing special soundness and zero-knowledge properties. From the verifier's response, equations 4a to 4d are derived, involving commitments CD, CS, and quart. These equations define RS, RT, and S in equation 5. Dividing equation 4a by 4b and equation 4c by 4d yields equations 6 and 7, demonstrating that S, RS, is an opening of the commitment CS, and S, Y, RT, is an opening of the commitment quart. The paper then explores zero-knowledge proofs for arithmetic operations in the finite field F, leveraging the sum-check protocol, specifically the GKR protocol. This protocol relies on the multilinear extension of a d-dimensional tensor S, expressed as a multivariable polynomial S via transformation. The polynomial S, defined in equation 8, satisfies the interpolation property in equation 10. The multilinear extension enables the verification of arithmetic operations between vectors to be rewritten as the verification of the sum of a multivariable, low-degree polynomial G, as shown in equation 11. This development sets the stage for efficient zero-knowledge proof protocols for arithmetic operations. The sum-check protocol's use of the multilinear extension allows for the verification of arithmetic operations to be performed efficiently, without revealing the underlying values. The protocol's reliance on the interpolation property and the transformation of the tensor S into a polynomial S enables the verification of complex arithmetic operations. The development of this protocol is a crucial step towards the creation of efficient zero-knowledge proof systems for arithmetic operations. The sum-check protocol, also known as the GKR protocol, is described in algorithm 2. This protocol verifies equation 11 over V rounds. In the first round, the prover sends a polynomial G1, x1, and claims it equals the sum of G, x1, x2, x underscore V, over all possible values of x2, x underscore V. If true, H equals G1, 0, plus G1, 1. The prover then proves equation 12 holds at a random point R1, leveraging the Schwarz-Zippel lemma. In the second round, the prover sends a polynomial G2, x2, and claims it equals the sum of G, R1, x2, x3, x underscore V, over all possible values of x3, x underscore V. If true, G1, R1, equals G2, 0, plus G2, 1. The prover then proves equation 14 holds at a random point R2, again using the Schwarz-Zippel lemma. This recursive argument continues until the final round, where all claims can be proved with high probability if and only if GV, RV, equals G, R1, R2, R underscore V. The verifier can easily verify this by opening the commitment to G. The protocol's completeness is straightforward by construction, while soundness follows from the recursive application of the Schwarz-Zippel lemma for each round. The zero-knowledge property follows from the Peterson commitment's privacy guarantee. Figure 3 illustrates the protocol's procedure. Linear layers can be reduced to the sum-check protocol. These layers can be written as matrix multiplication, interpreted as functions FA, FB, FC that map binary representations of indices to elements of a field F. The multilinear extension of these functions can verify the execution of linear layers using the sum-check protocol. Specifically, equation 19 is in the form of equation 11, allowing the sum-check protocol to be applied with a log2n variant, degree 2 polynomial G, B, and H equals FFC, I1, I underscore log2n, J1, J underscore log2n, at a random point, I1, I underscore log2n, J1, J underscore log2n, element of flog2n times flog2n. The authors propose a zero-knowledge proof system for non-arithmetic operations, focusing on reducing ReLU activation to bit decomposition. Bit decomposition is a commonly used technique for zero-knowledge proofs of non-arithmetic operations. In the context of ReLU activation, the authors define the pre-activated tensor Z and the after-activated tensor A, computed as the elementwise product of the sign and absolute value of Z, as shown in equation 20. To facilitate this, the authors describe the sum-check protocol, an interactive protocol for evaluating polynomials, outlined in algorithm 2. This protocol consists of three main stages: commitment, evaluation, and verification. In the commitment stage, the prover commits to a polynomial G and sends the Peterson commitment to the verifier. In the evaluation stage, the prover computes polynomials G1, G2, GV with arguments x1, x2, xv and sends them to the verifier. The verifier checks whether the received polynomials satisfy the required conditions, and if not, outputs reject. This process is repeated for I equals 2, 3, v. In the verification stage, the verifier checks whether the final polynomial GV matches the opening of the commitment by a proof system in algorithm 1. If it does, the verifier outputs pass, otherwise, it outputs reject. Figure 3 illustrates the sum check protocol for H equals P. This protocol is crucial for enabling zero-knowledge proofs of non-arithmetic operations, such as ReLU activation in neural networks. In foundation models, reducing non-arithmetic operations to arithmetic ones is crucial for implementing zero-knowledge proofs. The authors of this paper present a novel method for achieving this reduction, specifically designed for operations like ReLU activation functions and softmax layers in neural networks. Their approach utilizes bit decomposition to represent a number z as a qubit binary vector, z0, z1, zq. By applying the Hadamard product and elementwise absolute value, an arithmetic representation of the original non-arithmetic operation is obtained. This representation accurately recovers the original value of z. Furthermore, the authors demonstrate how to execute the reduced arithmetic operation using the sum check protocol, ensuring that the resulting operation can be evaluated and verified securely. However, for large prime orders P, this method requires an unwieldy binary representation. To alleviate this, the paper proposes using lookup tables to simplify the process. By maintaining a shared table between the prover and verifier, containing input and output vectors for a given non-arithmetic operation, the prover can demonstrate that the input and output vectors satisfy certain subset relations. These subset relations are reduced to a sum check proof using logarithmic derivatives and rational functions, yielding an efficient proof. Integrating this methodology into zero-knowledge proof systems for foundation models is essential for constructing models that meet real-world deployment demands. Notably, transformer and multi-layer perceptron (MLP) models consist of layers requiring arithmetic operations, where secure computations of non-arithmetic functions like ReLU activation are paramount. A general framework is proposed, where individual components comprising linear layers and operations requiring lookup table outputs must undergo explicit implementation procedures defined through standard gate operation setup techniques along strict conversion expressions comprising protocols encapsulated systematically like reintroduce efficient optimized addition control operators governed locally combined sequentially synthesized rules giving wide expressions unified handling addition. Original assumptions laid focus defining first by its parameter n integer through logic 0 definition q meaning related constants domain including equations properties referenced utilizing structure values producing generated example. Thus parameters modeled protocol including modular q computational parts involving form main decomposition real using complex protocols equations along relations implementation solving setup examples setting. All encapsulation solutions within rational fully output operation efficient reduced within referenced-based sharing utilizing expressed techniques performing thus decomposition forms yielding low initialized action date handling formal extended additional, particularly governing evaluation problem to efficiency existing security verified implementations layer basic structures part complexity level equations constructed application detailed reviewed current expressed throughout wide constructions generated values depending introduced context efficiently considered constructed particular details efficiently composed setup maintaining combined applying process evaluating constructions directly component within one direction outlined assuming local availability. In Table 2, an overview of zero-knowledge proof techniques for various operations in foundation models is presented. SumCheck protocol is utilized for linear layers, convolution, and residual connections, while lookup tables are used for softmax, sigmoid, and other activation functions. Bit decomposition is employed for piecewise linear activation functions like ReLU. Notably, ZKLLM is the first work to introduce zero-knowledge proofs to foundation models with tens of billions of parameters. The authors propose ZKDPS, a zero-knowledge decentralized proof system for large language models, built upon ZKLLM and ZKDL. However, speed remains a significant challenge for zero-knowledge proofs of foundation models. For instance, Generating a proof for Llama 213b with an input token length of 2048 takes ZKLLM roughly 15 minutes, whereas vanilla inference takes less than 0.1 seconds per token. To accelerate proof generation, ZKDPS proposes leveraging the compressible property of LLMs through algorithmic innovation. One approach involves using a small draft model to guess the output of the original LLM, similar to speculative sampling. Experimentally, the top one guessing accuracy of the draft model reaches as high as 82% in Eagle, a state-of-the-art speculative sampling method. Another approach is to leverage hardware acceleration of modern GPUs. ZKLLMs has already utilized CUDA implementation to parallelize computations in proof generation. The authors are optimizing CUDA kernels using engineering methods like tensor parallelism and KV cache. Furthermore, they introduce sequential vector encryption, SVE, a robust encryption scheme inspired by their diagrammatic interpretation of homomorphic encryption applied on select linear layers rather than the full model. SVE focuses on modern LLM architecture, where the LLM is considered a sequence of vector space operators. Each operator output contains information about both the input and output of the model, referred to as a latent representation vector. Secure vector encryption, SVE, is a technique implemented in large language models, LLMs, to enhance security by obfuscating intermediate vector representations. This method ensures that any observation of these representations cannot be used to extract sensitive information from either the initial model input or output. The SVE technique involves randomly transforming the outputs of every operator in the sequence of LLMs, making it difficult for an attacker to interpret the intermediate latent spaces. For linear operations, the transformation process involves multiplying the original matrix representation of the operator with invertible transformation matrices. Nonlinear operators, such as ReLU, can be transformed by leveraging their symmetries, specifically their commutative properties with certain transformations like permutations and scalar multiplications. The transformation process involves concatenating multiple transformations, resulting in a final transformation matrix T that encapsulates the entire encryption process. However, revealing this matrix directly would compromise security, so a form of secret sharing is employed to keep the transformation matrices obscure. This method ensures that the computational outputs of the original model are preserved while maintaining the confidentiality of the encrypted representation vectors. The implementation of SVE in LLMs provides a novel approach to enhancing security in machine learning models, particularly in scenarios where data privacy and confidentiality are paramount. Secure vector encryption, SVE, is enhanced by incorporating secret sharing, which is achieved by transforming a linear-nonlinear pair of operators, a fundamental structure in most neural network layers, including large language models, LLMs. Specifically, the original ith layer bias bi is represented as bi equals raw, where A is a linear transformation and R is the nonlinear ReLU function. By applying transformations S and T, the bias can be rewritten as bi equals T1RC, where C equals TSA is a new matrix transformed from A. This transformation enables the output of the previous block to be transformed according to S1, and the output of bi to be equivalent to the output of bi transformed by T1. To prevent the transformation pair S and S1 from being recovered by an agent, the transformation T1 is made recoverable, allowing S to also be recoverable with public knowledge of A by looking ahead to the next layer bi plus 1. The appropriate transformation pair U and U1 can be inserted, absorbing U1 into the linear representation for bi plus 1. This results in the layer bias being transformed as bi equals UT1RC equals GRC, where G equals UT1. To mitigate potential attacks from colluding agents, additional transformations are injected in the sequential chain of operators. These additional operators are sent to a trusted third party or the original client to sequentially encrypt the representation vector, ensuring that the encrypted outputs are always passed back to the holder of the additional transformation. In general inference scenarios, the consensus-based verification check (CBV) strategy is employed to ensure model verification and integrity. This approach leverages the collective agreement of multiple nodes to ensure the correctness and integrity of model execution without revealing sensitive data. Additionally, split learning (SL) is used to maintain data privacy by dividing the model into segments and training each segment on different nodes, ensuring no single node has access to the complete dataset. Figure 4 illustrates the security flow of general inference at Nesa, which first applies SL to encrypt the first few layers to encrypt the raw data, followed by sharding and deployment of AI models to nodes with redundancy. The Nesa system employs a consensus-based verification (CBV) mechanism to ensure the integrity of AI model execution across decentralized nodes. This approach involves 4 steps: redundant execution, output collection, consensus determination, and verification and finalization. In this process, a subset of nodes independently computes the output for the same input, and the outputs are collected for consensus evaluation. A consensus algorithm is then utilized to determine the agreed-upon result, which is considered valid if it satisfies a predefined criterion. The system's security flowchart illustrates the integration of CBV for model verification and split learning (SL) for data encryption and user privacy protection. The goal is to ensure that all nodes accurately execute the model, yielding consistent outputs. The consensus-based approach facilitates the verification of model integrity across decentralized nodes and introduces a robust mechanism to detect and mitigate the impact of faulty or malicious nodes. In Nesa's decentralized system, ML models' computational graphs may be sharded across multiple nodes for scalability. Each node possesses a unique shard of the complete model, requiring a specialized approach to consensus-based verification. Given an input X, the execution of these shards across K nodes produces a set of partial outputs, where each output is computed using the corresponding model shard. The verification process involves evaluating the consistency of these partial outputs to ensure the integrity of the complete model. The mathematical formulation of the consensus-based verification process is provided in equations 30 and 31, which describe the redundant execution and consensus determination steps, respectively. These equations formalize the process of achieving consensus among nodes, ensuring that the output of the AI model is accurate and trustworthy. The system's performance and security are evaluated through a combination of theoretical analysis and experimental results, demonstrating the effectiveness of the proposed approach in ensuring AI model integrity in decentralized environments. This approach enables scalable and decentralized AI model execution while maintaining robust verification mechanisms, making it suitable for applications where data privacy and model integrity are paramount. Consensus-based distribution verification (CDV) is a novel method for enhancing the security and privacy of distributed machine learning models. In a decentralized network, where models are sharded across multiple nodes, CDV verifies the integrity of model executions through a 3-phase process. First, shard redundant execution is performed, where each shard of the complete model is computed by a designated subset of nodes. This introduces computational redundancy, facilitating cross-verification among nodes computing the same shard and enhancing the detection of discrepancies or faults. Next, redundant output collection and verification are performed. Outputs from each shard are collected and evaluated using a consensus mechanism specific to that shard, determining a shard-specific agreed-upon result and ensuring the integrity of the shard's computation. The shard-specific consensus results are then combined to reconstruct the final model output, ensuring the integrity of the complete model execution. In the final phase, CDV assesses the statistical distribution of model outputs across the decentralized network. Advanced statistical analysis is performed, deriving metrics such as the mean, standard deviation, and potentially higher-order moments. Non-parametric statistics may also be incorporated to capture the full essence of the output distribution. The derived metrics are then compared with predefined benchmarks or dynamically established norms using sophisticated statistical methodologies, including hypothesis testing, divergence measures, or similarity indices. This facilitates an objective assessment of model integrity, enhancing security and privacy without direct comparison of individual inference results. The consensus mechanism with adaptive thresholding is a crucial component of the CDV framework, enabling nodes to collectively determine the acceptability of observed distributions in alignment with benchmarks. This mechanism dynamically adjusts sensitivity based on historical data and operational context to identify deviations that signify integrity breaches. By focusing on distributional characteristics rather than discrete output values, CDV offers a powerful solution for verifying the integrity of distributed machine learning models in Nesa's decentralized framework, aligning with the goals of enhancing model security and maintaining stringent privacy standards. To facilitate secure and efficient computation on encrypted data, split learning is adopted as a pragmatic solution. This method partitions the computational model, allowing for data to be processed in parts without revealing sensitive information. In split learning, user data is protected by not being directly transmitted to any nodes, with only data embeddings being passed around. Each node only accesses the embeddings of certain layers. Mathematically, the split learning process can be described using a neural network model composed of a sequence of layers, where the input to the network is x. The output of the ith layer is given by equation 35. Assuming the model is split at layer k, the client computes the intermediate representation z as per equation 36, which is then transmitted to the server. The server continues the computation as per equation 37. The loss function computes the error between the network output y and the true labels ytrue, and the gradient of the loss with respect to the model's parameters is computed through backpropagation as per equation 38. To address privacy concerns during the transmission of z from client to server, differential privacy methods may be applied, with a proof of privacy preservation demonstrating that the information leakage remains below a threshold as per equation 39. This approach ensures that the CDV framework maintains stringent privacy standards while verifying the integrity of distributed machine learning models. Nesa's decentralized inference system for large language models, LLMs, is designed to enhance user data confidentiality and integrity through the use of split learning, SL, and differential privacy. This approach ensures that only encrypted data fragments are shared among nodes, reducing the risk of data leakage. The incorporation of differential privacy allows for a balance between privacy preservation and computational feasibility, making it a tunable parameter based on user requirements. In addition to SL and differential privacy, Nesa utilizes trusted execution environments, TEs, to establish robust security and privacy measures within its decentralized architecture. TEs provide an aggressive isolation mechanism, safeguarding sensitive processes and data from unauthorized access, including node operators themselves. They offer three primary benefits: isolated execution, data privacy, and consistency and integrity. Isolated execution ensures that computations within the TE remain protected even if other parts of the node are compromised. Data privacy is ensured through encryption of data inside the enclave, maintaining confidentiality when data is shared across nodes. Lastly, consistency and integrity are ensured via cryptographic techniques such as attestation, which proves that computations were performed correctly without revealing underlying data. CPU and GPU-based TEs, including those from Intel, AMD, and NVIDIA, are integral components of Nesa's framework. Specifically, NVIDIA's GPU TEs support high-performance computing tasks securely, efficiently handling tensor-based operations. The general procedure involves initializing a CPU TE virtual machine, which then controls the GPU TE, providing an additional layer of security. By leveraging TEs, Nesa can effectively provide robust security and privacy measures essential for both critical and general inference scenarios. This ensures that sensitive data and model parameters are always protected from unauthorized access and tampering. A specialized version of TEs, named NTEE, is designed to best suit Nesa's scenarios with decentralized inference, making it feasible for all node runners with or without GPUs. Nesa, a decentralized AI provider, harnesses the collective hardware capabilities of multiple node runners to perform AI inference for users. To ensure both secure and efficient computations, Nesa employs the novel Trusted Execution Environment (NTEE) approach, which leverages trusted execution environments (TEs) for both CPU and GPU. This setup provides a secure computing environment with minimal performance overhead, maintaining high performance in both critical and general inference scenarios. NTEE implementation involves initializing a blank virtual machine T on each node runner, followed by remote attestation to verify that the node runner's machine meets NVIDIA's-T requirements. After verifying the evidence, the orchestrator determines whether each node supports GPU-T or CPU-T only, and initializes the appropriate VM accordingly. By leveraging hardware-based security, NTEE eliminates the need for algorithm-based security measures, resulting in faster performance. Furthermore, Ts enable secure collaboration across multiple nodes by creating isolated enclaves that protect data during computation, making it ideal for Nesa's decentralized AI inference tasks. This approach ensures secure and efficient computations, even in a decentralized environment. The Nesa framework's decentralized AI inference paradigm, NTEE, is depicted in Figure 5. This process begins with the orchestrator dispatching a blank virtual machine, VM, to each node, followed by remote attestation to verify the types of trusted execution environments, Ts, supported by each node. The attestation process entails verifying the T types and requirements with the server provider, such as NVIDIA, to ensure the node can support specific Ts, including CPU and GPU Ts. Upon successful attestation, the orchestrator sends user data and AI models to each node's Ts via a secure channel. The nodes then execute AI inferences within the Ts, communicating with each other via secure channels. Finally, the orchestrator retrieves the aggregated results from the Ts securely and notifies the node runners to destroy each T. The secure data and model transmission process, denoted as Step 3, involves transmitting the user data X and AI model fragment MI to the node runner's T via an encrypted channel, utilizing a secure transmission protocol similar to SSH. Secure transmission. ENS, X, MI. SSH right pointing arrow TEE. This process ensures the confidentiality and integrity of the data and models during transmission. The Nesa framework's use of Ts provides a secure environment for AI inference, enabling the execution of AI models on remote nodes while maintaining the confidentiality and integrity of the data and models. The decentralized nature of the NTEE paradigm allows for the distribution of AI inference tasks across multiple nodes, enhancing scalability and efficiency. The figure illustrates the sequence of steps involved in the NTEE paradigm, including the initialization of Ts, secure data and model transmission, AI inference execution, and secure retrieval of results. The use of Ts and secure communication protocols ensures the security and confidentiality of the AI inference process. The Nesa framework's support for multiple T types, including CPU and GPU Ts, allows for flexibility in the deployment of AI inference tasks. The framework's ability to adapt to different T types and requirements enables the efficient execution of AI models on a variety of hardware platforms. Nesa's decentralized AI system operates in a unique setting, leveraging multiple trusted execution environments, Ts, across various nodes to run shards of an AI model. This approach requires advanced strategies for efficiency and security. The system initiates with the user sending encrypted data and model fragments to the orchestrator, which then distributes them to node runners. Each node runner's T performs a part of the AI inference using the model fragment on the data, ensuring confidentiality and integrity through encrypted channels and secure computation within isolated environments. To optimize communication among multiple Ts, the orchestrator sets up encrypted channels among nodes with computation dependencies, allowing direct communication between Ts for intermediate inference results. This approach reduces bottlenecks and enhances the speed of decentralized inference processes, crucial for real-time applications. After the final computation is completed, the final inference results are securely transmitted back to the orchestrator using an encrypted channel. Once the inference results have been successfully retrieved and verified, the T on the node runner is destroyed, ensuring that any residual data or model information is completely removed from the node runner's hardware. Nesa's innovation lies in minimizing data transfer between the orchestrator and each T by establishing preset secure communication channels among the Ts. This direct communication is secured using encrypted channels to ensure data privacy and integrity during transit, and the owners of the nodes cannot access the communication. This approach significantly reduces latency and improves overall system efficiency, making it suitable for real-time applications. In a decentralized AI inference setup with K-node runners, each equipped with a trusted execution environment, the process of establishing secure communication channels among the required Ts is optimized for sharding. This approach enhances security without unnecessary complexity. The Ts, being attested and verified, can establish secure communication channels using a key exchange protocol, such as the Diffie-Hellman key exchange. Each pair of Ts generates a shared secret key, which is then used to derive a session key using a key derivation function, KDF. The session key is used to encrypt data transmitted between Ts, ensuring confidentiality and integrity. Nesa's system employs a dynamic scheduling strategy to manage heterogeneous Ts, which vary in type and computational power. This strategy is based on initial attestation results, determining whether a node supports GPU-T or CPU-T only. The goal is to leverage the strengths of each type of T, ensuring computationally intensive tasks are handled by more capable nodes, thereby optimizing overall system performance. The dynamic scheduling strategy involves three innovative steps: initial attestation, resource allocation, and execution and communication. Initial attestation determines the capabilities of each node, identifying GPU-T or CPU-T support. Resource allocation assigns different shards of the AI model to different Ts according to their computational capabilities. Execution and communication establish encrypted channels for direct communication between Ts with computational dependencies, reducing the orchestrator's load and improving efficiency. The innovations in Nesa's use of Ts are driven by several key motivations, including security and privacy. Ensuring the confidentiality and integrity of user data and AI models is paramount. By using Ts and secure communication channels, Nesa guarantees that sensitive information is protected throughout the computation process. Nesa optimizes efficiency and performance by dynamically scheduling computational tasks across heterogeneous trusted execution environments, Ts, ensuring efficient resource utilization and minimizing delays. This approach enables seamless scaling without compromising performance or security. Nesa's innovations effectively manage decentralized AI inference processes, providing secure, efficient, and optimal performance across diverse Ts. In addressing security and privacy concerns in distributed and decentralized computing scenarios, Nesa offers adaptive solutions tailored to different scenarios. For critical inference tasks, zero-knowledge decentralized proof system (ZKDPS) and sequential homomorphic encryption (SHE) are recommended. For general inference tasks, consensus-based verification (CBV) and split learning (SL) are proposed. Nesa's Trusted Execution Environment (NTEE) provides a hardware-based approach that addresses both verification and encryption needs simultaneously. Future research directions include optimizing ZKDPS to reduce computational overhead, developing zero-knowledge proof templates for various AI models, and building an automated framework to recommend and choose the best set of security and privacy approaches based on specific user needs and application scenarios. This framework will enhance user experience by providing customized, optimal security solutions. I'm happy to help. However, it seems that the transcript provided is incomplete. There is no content to refine. Please provide the complete transcript, and I'll be happy to refine it according to the guidelines provided. Research and privacy-preserving training of machine learning models has led to the development of various techniques, including split learning, differential privacy, and trusted execution environments. Tanveer Khan et al. Introduced split learning, a method for training models on encrypted data while maintaining privacy, which is relevant to the current research on privacy-preserving fine-tuning of large language models. The Llama 2 framework, providing open foundation and fine-tuned chat models, serves as a reference point for large language models, although it is not directly related to the current research. Differential privacy, a concept introduced by Cynthia Dwork, is a crucial aspect of privacy-preserving machine learning. Ruzba Benia et al. proposed UTUN, a framework for privately fine-tuning large language models using differential privacy, which is closely related to the current research. Trusted execution environments, TEs, are another essential concept in privacy-preserving machine learning. Stavros Volos et al. Introduced Graviton, a framework for TEs on GPUs, enabling secure execution of machine learning models. Fan Mo et al. Proposed Darknets, a framework for model privacy at the edge using TEs. The concept of secure communication over insecure channels, introduced by Ralph Merkle, is fundamental to the development of privacy-preserving machine learning algorithms. This concept is relevant to the current research, which focuses on developing secure and private fine-tuning methods for large language models. The cited works demonstrate the importance of differential privacy and TEs in privacy-preserving machine learning, highlighting the need for secure and private fine-tuning methods for large language models.